Okay, before that, I want to hear your feedback about the test one. I need to grade the test
I did.
today. Get ready.
Okay.
You see your score sometime today. Doctor.
I can help you.
So I really want to hear your feedback. I'm a very friendly person. Your test is gonna be based on your feedback. Okay. What do you feel about test? Do you see anything outside the topic that we discussed? Do you think anything outside the format we discussed? We had a revision class, revision lecture. Basically, I went through the last year, test question, and then even I send you an email, hey, bring that Scantron, bring calculator, focus on all the topic we have done so far. Even I marked the yellow color if you see the email, because that's the input I could give to you guys. Now, I want to hear your feedback. As I told you, the test is gonna be based on your feedback. What you think about test one. Anyone want to give me feedback? Everyone's happy with the whatever?
Can we get extra credit on the test?
I mean, I haven't graded yet. Yeah.
I was gonna say, we went over the double split and everything in class before the exam, but the homework being due today, having the extra practice with those questions on the exam, I think that was a little bit tricky. Even though we went over that in class with the homework.
That's the reason I sent an email, right? So I sent an email. You guys gonna get confused. So I sent an email. Hey, even like if you open that email, group email, I highlighted that. I can send. Show you over there. But I highlighted that point. Hey, please go through all the content we have gone so far. Okay. So that's the reason I highlighted that part. So obviously your performance is a whole. So how you? This is I told you that test was going to be very easy. The test is going to be a little bit comprehensive, the final is going to be comprehensive, right? So I told you the complexity of the exam going to increase. So if you think that you're falling far behind, please think about how much effort you have to put on this class. Any further comment? If you do not tell me, I'm just gonna follow the same pattern, right? Any other further comments you want to have? I just graded your, Scantron. The Scantron looks good. Okay. I'm pretty sure that some of you guys are gonna get, a couple of students gonna get 100 out of 100. Okay. So because whenever I grade the Scantron, the machine gives you no error, that means you have 100 out of 100. So at least 3 students gonna get 100 out of 100. Now there will be many 90s, okay? So that's my expectation. So whenever I grade, so I need to put the number after the scatter is graded. So no comment, right?
Could you post solutions to the homeworks after they're due so we could study them for the exams?
The homework?
Yes, the solutions after they're due.
So that's a thing I can ask to the grader.
Okay.
And you have a plenty of resources. If you want to, one thing I really surprised. We have our office hour, and no one show up in the office hour. I'm not saying this class, but in other class, they show up I'm teaching general physics too. They show up, in the office hours, they even go through the class they miss because they have to travel. But from this class, I have not seen a couple of students. They show up. I think he was in my office. Couple of, but the office hours is for you. Okay, reach out to me. we have a health lab and we have plenty of resources around. So please utilize them. As I told you, physics 2 gonna be a little bit challenging compared to physics 1. The topic we're gonna go through is light, electricity, magnetism, electromagnetism. Those topics are really challenging. So I told you in the beginning of the class, physics 2 is difficult compared to physics 1. So please pay attention from the beginning of the class. Okay.
Will we be getting our tests back?
Test back?
Like our paper copies?
No, you will not get test back, but you can visit my office and take a look on your test. You can review your test and you can figure out what is the minor mistake you have made. Most of the mistake, I'm pretty sure that they're gonna be minor mistake. Okay? So there is just some student who missed the test because of the travel or something like that. Otherwise, I can tell you what is the minor mistake you have made over here. So I don't care right now, but there are a couple of mistakes you guys made. Very minor mistake. One of the mistake I can tell you that. I went through the convex mirror, and many students are asking me a question. Hey, it should be negative some number. I'm asking the object distance, not image distance. And you are asking me, hey, it should be negative number. Object distance cannot be negative at all. I mean, there's only one number that is positive. I could just go with that. Even I will not do any calculation if I were you. Right? So basically, those are the minor mistakes. You will realize that. Okay. So anyway, so I don't like to spend too much time because there are some students who need to take a test. So I won't give like all the information. But later on, whenever you come to me and then review your test, you'll find, oh, no, I shouldn't have like a made this mistake, something like that. Okay. So anyway, I'll see your whole performance, but there will be a couple of hundreds and there will be a couple of 90s. I'm pretty sure about that. Okay. So with that, so I'll just briefly discuss about the another phenomena that proves that light is a wave. So from the beginning, I was telling you that light behaves as sometimes behaves as a particle, okay, and sometimes it behaves as a wave. Okay, and so we'll not discuss about this particular nature of light in our class, but we mostly discuss about the wave nature of the light, and one of the phenomena that describes the Young's double slit experiment. We just Young's double slit experiment, and the second one is, this is another phenomena, diffraction. So diffraction of light, okay? So basically diffraction phenomena happens if the light passes through the single slit, okay? You don't have to have even like a double slit to see the diffraction pattern. So if the light passes, there are like other kind of diffraction, but we're going to talk about the one single slit diffraction. That means if the light passes through a single slit, okay, then if this slit, the width of the slit is very small, it should not be like a very big slit. If the slit is very small, then if the light passes from this slit, then if you place a spectrum or like a screen, then you will see the spectrum even if light passes through the single slit. Okay? There is no interference because the interference means that superposition of two waves. Right? But here there is only one source that is passing through the slit. The single slit diffraction. Okay, there are other kind of diffraction also. We are not going on that. But even like pass to the single slit, you will see the spectrum. There's a little bit difference between the Young's double slit and this diffraction, because the width of the maxima and minima will be different. The width for the maxima and minima, you can see that the central maxima over here, similar to the light, whenever you pass through the this single slit, you see the central fringe is maximum. Okay, the central fringe is maximum, and it has a bigger width. The intensity is higher. Okay, and if you go to either left or right side of this maxima, the width decreases, the intensity also decreases. Okay, this is the typical phenomenon. And if you use the red light, definitely you have a central point, it's a maximum, and it's a red color. And there's like a green color over here. So basically you have like a green light is passing through the screen. So basically you have central maximum is green, but there's like in between these two green fringe, you have a dark fringe over here. Okay? You have an alternative maximum, minimum point over there. Okay? And so there's one question, I asked about monochromatic source. And even then some of the students, they made a mistake. How many colors in a monochromatic source has? I literally wrote over here, monochromatic. Chrom means color. Chromosome, it's like a color. Mono means one. And there's like some different I wrote 7 colors because the white light from the sun, it has a 7 color. I want to confuse you guys, whether you know monochromatic or not, but even then you made a mistake. I literally wrote, if you take a look on your class note, if you're in the class, so I really surprised that, that means you do not pay attention. It's a general sense, like mono means one. Chrom means color. You have a light that has the same color, there's a single frequency, single wavelength, then we call monochromatic, and whenever we discuss about the diffraction and interference fringe, we always pass the light of monochromatic source. Because if you have a different color, that means you have a different frequency, you have different wavelength, so the interference fringe or diffraction fringe won't be clear. Okay? You will not see it. So that's the reason that we use a monochromatic source. So anyway, so this is the one of the things that you have to pay attention. The light is passing through the single slit, and you have a single slit. It's a let's say narrow slit. Okay, you have a slit over here. Let's say you have a single slit of width A. Okay, and whenever it's a physical barrier, it's a single slit, okay? Then light is passing through the slit, like that. So you will see a maximum and minimum pattern on the screen, okay? The central point of this screen, you always see maxima, or we call bright fringe, maxima or bright fringe. So people use bright or maxima. The meaning is same. You have a minima, you have another maxima over here, maxima. So this is central maxima, n equal to 0, you have a false maxima, okay? False or maxima, okay, maxima. So bright, you have a minima over here. So basically, you have maxima, minima in the alternative fringe. You can have either below or above this screen. And so the one of the condition that the diffraction phenomenon happen from a single slit is that the width of the slit has to be comparable with the wavelength. Okay, this is very important point over here that for the diffraction or interference to happen, the width of the slit, the width of the slit has to be comparable with the wavelength of the light. And you know that wavelength of light is very small, of the order of Armstrong nanometer, or like sometimes micrometer. Okay, so this is like 10 power minus 9 meter. It's a very small slit. In other words, this width of the slit has to be very small. If you have like let's consider that you have like this room is dark, and if you send the light from outside to this small narrow opening, you will see the print on the wall of this building. So you can do it even like at home. But the width of the slit has to be very, very narrow. Okay, this is the function for the diffraction of light, and it's a very similar. You don't have to go through like detail. So you have the distance between this screen and the single slit. You can use the same method, same way to describe this one. So you can derive the formula. I'm not going like in a detail. Basically, you can divide the slit because the light going from this point, the light is going to this point. They meet somewhere here. And they make a what kind of maxima or minima. So basically, there's a trick how to do it, and you can again do the perpendicular, and you can also find the path with delta L over here. So this is a trick you have to do it, but I'm not going in that detail. So you can see that light. You can divide the width in like a different parts over here, and if you consider like a for first minima point over here. So basically, like you can consider, you can divide the whole width in the two parts, and then you can consider light is going from the upper part of the slit and the midpoint of this one. Then you can find the function for the maximum. So I'm not going into like a detail, but just I'm gonna write the condition for M minima. So if you have so M minima. Condition for the M minima is you have A sine theta equal to M lambda. The M value is going to be 0. It should be not 0 because the minima point, the central point is always maxima. So you have an N equal to 1, 2, 3, equal to 8. So this is the condition for M minima to see on the screen. So you can have like some random point, and then what is the condition for the M minima? Okay, so you can use this equation. Okay, A is the width of the slit, and theta is the angle. That the light makes the horizontal direction. Okay, some people say theta is the angle of diffraction. It's the same thing. Angle of diffraction. Theta is the angle of diffraction. M is the order of minima. If M is 1, you have first minima, M equal to 2, second minima, and so on. Okay, and lambda is the wavelength of the light. So you can derive this formula easily by dividing the slit and finding the path difference. That is what we did for the Young's double slit experiment. Okay, so and we don't have to go through all the details. So I have one problem for you guys from the diffraction. This is exactly similar to the Young's double slit experiment. So I just give a hint and then finish the topic. We need to move a little bit faster also. Over here, a monochromatic source of light. Again, monochromatic source. Okay? So we are using the monochromatic source of light that has a wavelength of 441 nanometer. See? The wavelength of light is of the order of nanometer. So you have the light is passing through a narrow slit. So don't be confused. This is the figure you have to make. So it's a narrow slit means you have a single slit diffraction. You have a light that is passing through a single slit. Single slit. Single slit. Light is passing through a single slit and maybe even like a slit. Doesn't matter. It's like it's a narrow, right? Okay, you have a single slit. Do not make a double slit, okay? Light is passing the single slit over here, and on the screen that is 2 meters away. So you have a screen that is 2 meters away. The screen, okay, that is 2 meters away. Okay, the center point is always maximum. Okay. On the screen that is 2 meters away, the distance between the second diffraction minima and the central maximum. You have a second somewhere here. So center of and this is a maximum. The n equal to 2. Okay. And the central maximum. Central maximum is n equal to 0 definitely, right? N equal to 0. Central is like you are starting from there. On the screen that is 2 meters away from the distance with the central, between the second diffraction minimum and the central maximum is 1.5 meter. 1.5 centimeters. So delta y is given, let's say delta y is 1.5 meter, centimeter. Like that. Okay. The light is going from here and diffraction is happening over here. You have some angle theta, the angle of diffraction, right? Calculate the angle of diffraction. You need to find theta value. Right? It's like a simple. You have this distance is given. This distance is, I just say capital D, and then you can call the 2. What is the value? 2 meters away, sorry, 2 meters. Can you calculate theta? You have right angle triangle. This side of the triangle is given. This side of the triangle is given. Can you calculate theta? Yeah. Tangent. And once you find the theta, find the width of the slit. So we have a 1:2 formula. A sine, so there is a 1:1 formula is m lambda. M lambda. I need to find width of the slit, which is A. So I know what is theta value. I know what is the m value. What is the m value? 2. Is the second. So you have lambda is given. So over here, A equal to m lambda divided by sine theta. The theta you got from the part A using the trigonometric function. M is 2, lambda is given, and sine. Whatever the theta value you get over there, you can just get the A, the width of the slit. Okay. So I didn't do like everything like a bar. This is the similar problem like we did for the interpreters. Okay, you have trouble here. Yeah.
How'd you get m is equal to 2?
M equal to 2. This is for the second minimum. Second minimum is like a m represents the order, right? This is first minimum, second minimum, third minimum. Okay. So if it says second, that means you have m equal to 2.
Oh, okay.
Okay, so it's an order. Okay, so we spend a lot of time on the optics, basically light. Now we need to go to another interesting thing. That is a diffraction grating. It's like you have a, you have a diffraction. You have a lot of this is slit. I'm not going into details, but if you are in optics, you have a diffraction grating. You have a width that is like a distance between the slit, and you will see the fringe over here. We don't go over in detail about this diffraction grating. The diffraction grating is like a one. We have a single slit over here, but this device has so many single slits, and you see the interference fringe on the screen. So I'm not going into detail about this one. I want to go to the chapter 21st. That is the one I want to start today. Coulomb's law. Okay. So this is the one of the very important point, very important topic in your syllabus. So far we were discussing about the optics. In the optics we talk about the different kind of optical phenomena. We talk about reflection of light, refraction of light, and we also talk about the different kind of mirrors, plane mirrors, concave mirror, convex mirror. We also talk about the different kind of lens, converging lens, diverging lens, and we also spend time on Young's double slit experiment, and this is the single slit diffraction. It was a really long topic, so we want to finish that topic now and start something new. Okay, this is also a very long topic. So this chapter is talking about the Coulomb's law. And before starting the Coulomb's law, we want to categorize whatever the materials we have in this world. In nature, we can divide in the three categories. Okay, so let's talk about these three different categories that we divide. So the first one is conductor, insulator, and semiconductor. Okay, so these three categories depends on how effectively they transfer the electricity from one point to another point. Okay, so first one is a conductor. Conductors, let's say you have a copper, platinum, and you have a semiconductor. You have a silicon, germanium, okay, and you have an insulator. You have an insulator, all are insulators. Insulators in nature, okay. Let's say glass. You can have a wood. You have a plastic. They are conductor. So, common example of conductor is, let's say you have a gold. The gold wire is very I can just say gold. So let's say gold wire, gold basically Au. Okay. So platinum, copper. So copper is very copper wise used a lot. There are many. Okay, platinum. They have a semiconductor. The semiconductor is a silicon. Okay, Si, germanium, and you have an insulator. There are many insulators. You have a plastic. There are insulator, plastic. You have a glass, and you have other something like that. Okay, there are many insulators. And the category, there's three categories. They are based on how effectively they conduct electricity from one point to another point. Okay. For example, conductors. You have a metal. Gold, platinum. Everything. Like if you take a look on the periodic table over here, they are like a metal. Usually have like in this category. So sodium also conductor. This rubidium, cesium, they are also conductor. So and semiconductor usually have like in this category. Silicon, germanium is over here. Okay, and I mean, the conductor is like iron, also nickel is conductor, and there are like many conductors over here. So, conductor, they conduct electricity from one point to another point, I mean, with a small resistance. With a small resistance. Okay? And insulator, they conduct electricity not at all basically. Insulator, if you have a plastic, let's say you have a plastic, if you have like, I mean, if you pass the current through this one, it doesn't pass through. Okay? And semiconductor means you have, your conductivity is not as good as metal, but it's not as bad as insulator. You are in between. Okay? So you can see that for our daily life, we use a lot. This one like you are, I mean, engineering people, most of you guys are from engineering background. So if you do experiment, whenever you use, even like in our lab over there, whenever you use, you have a copper wire because it passes the current effectively. Okay? And we use a lot. I mean, daily life, we have light, like there's electricity passing through it. Okay? So, so this is very useful in our daily life. I mean, we have a wood plastic also. I mean, we use for this one for insulating something. Okay? If you have like a wire that's like let's say you have a copper wire, but you can't toss copper wire with your hand. So you need to have something to insulate, right? So you use the insulator as well. You have to use the insulator. I mean, but semiconductor, silicon, germanium, compared to even like conductor and insulator, they are super useful. Super useful in the sense that, talk about silicon and germanium, you are already from the engineering background. Where do you use most this material? Silicon, germanium. Where you use this material? Silicon and germanium. Although it's like a conductivity is not as good as conductors. Why this material are so important? Anyone of you guys can tell me why this material is so important? Yeah?
In diodes?
You're using a diode, transistors, making chips, right? Transistor, everything, everywhere you use this material. Actually, I mean, there's the company based on this silicon, it's like a billions of dollars. Like one of the city in the United States called Silicon Valley. Silicon Valley, right? Where technology is there, you should have these semiconductors. Nowadays the car prices is going up because we have a shortage of chips, right? I mean, there's like many different devices, even your cell phone. You cannot have your cell phone without this semiconductor, because the chip is the major part, and then without semiconductor you cannot use it. Okay, so basically, although it looks like the conductivity of this one is not as good as conductors, they are super useful. Okay, so and another thing. So you have three categories mainly, and recently, I mean, I told you a while ago, there is one other class of material is called superconductor. You have a conductor, you have a superconductor. Superconductor. In the US, we use super a lot. I mean, if you are a common man, I am man. But if I am extraordinary, I am Superman. Right? If you are like a wave, you can break anything. You can break the building. You can kill thousands of people with one phone. Right? This is super. Okay? So over here, the definition is that you have some resistivity. Even if you have this kind of material over here, conductor.
No.
You have a conductor over here. Even you have Very good conductor, let's say you have copper, let's say you have a copper wire. So if you have a copper wire, over here, the temperature versus the resistance. Okay? The resistance gives the idea that how effectively it can transfer the current from one point to another point. Okay? If you have a low resistance value, that means you can pass the current easily. Okay? So if you have a conductor, let's say copper wire, and if you pull down like that, your resistance value decreases. So you have, let's say you have some like a 50 milliohms at room temperature. This is the, let's say, resistance value. The room temperature, you know, is a 300 Kelvin. You have a resistance value for the copper wire, let's say you have a 50 milliohm. It's a very small value, it's a milliohm, 10 power minus 3 ohm. If you pull down, you have a small value, that means it becomes like an effective, more efficient to conduct electricity if you pull down. But if you go to absolute zero, which is 0 Kelvin, that's the lowest temperature in this universe, you have some value. It might be maybe like a 1 milliohm, but it's not 0. Compared to 50 milliohms, your value is 1 milliohm. It's getting better for the copper wire, which is a very good metal that we use for the transferring the electricity from one point to another point. Now, if I have a superconductor, it's a conductor, it's a copper, it's a conductor. If you have a superconductor, what happens? You have some value, let's say, after some point, the resistance goes to 0. The resistance goes to 0. The point where the resistance goes to 0 is called critical temperature, and the critical temperature depends on what kind of material you are using. If you are talking about the mercury, or if you consider like a lead, it has a 7.1 Kelvin. If you go below this 7.1 Kelvin, you are basically having 0 resistance value. So if you have a 0 resistance value, basically you can pass the thousands of ampere of the current because there is no any resistance from the material. Okay? So this is conductor. So this should be much more better than the conductor. We call it superconductor. Superconductor. Okay? The superconductor. Okay, this is how they name. The person who discovered this material is Heike Onus from Netherlands in 1911. He discovered that, and I think I gave a little brief description about him. He was not trying to like invent this material. He was doing his own work, but sometimes locks comes into play. So basically, he was doing the experiment for mercury, and he found that the resistance suddenly went 0, and 0 even if he pulled down below that temperature, and he called that name as a superconductor. Okay, so there are a lot of story about that. He got Nobel Prize. He got like so much recognition after that. But long story short, a superconductor is a material that has 0 electrical resistance after the critical temperature. If you go below the critical temperature, it's 0. If you go above this critical temperature, it's not 0. And I asked a question last semester to the student, hey, a superconductor has 0 resistance above the critical temperature, and they didn't think about above or below the critical temperature, and then they got wrong. Okay, so basically the superconductor doesn't have a zero electrical resistance above the critical temperature. It's not like a normal metal, right? It has some finite value. It is zero only after you go below the critical temperature. So this kind of question you will see in the test. I'm pretty sure that this is going to be in your test. So even I tell you now, and then you write down in your class note, and you do not read that. Okay. So anyway, so I can spend like even like 1 hour to describe the conductor. Like I can go to atomic picture. Why conductor is like for example. So let me spend a couple of minutes. It's very interesting. Why like let's say you have a metal. You can consider about metal. Let's say sodium. Sodium, we have like a sodium over here, is a number, atomic number 11. Sodium, I represent as Na. It has an atomic number. So atomic number is 11. So if you have an atomic number 11, you can think of atomic picture, how the electronic configuration of this material look like. So let's talk about the how, if you have an atomic number 11, you have there are 11 number of electrons, 11 number of protons, right? Positive charge. Okay. So and this material has atomic mass of 23. You have a 12 number of neutrons. The neutron doesn't matter because neutron has zero charge. Okay. So if you see the atomic configuration, like one atom of this one, you have a nucleus, you have 11 protons, you have a 12 neutron, is a positive charge, and so this is a nucleus. If you take a look at the cell model, you have 2 electrons on the first cell, 2 electrons. So n equal to 1, you have 2. N equal to 2 has 1, 2, 3, 4, 5, 6, 7, 8. So you have 11 electrons, you have 10 is already gone. You have one more electron in the outer cell. I just like draw like this. You have one more electron in the outer cell. Okay, this is one electron over here in the outer cell. And this electron is loosely bound because this is the negative charge, you have a positive charge. You have a Coulomb interaction. That we're going to talk about that. The Coulomb interaction, the force between these two charged particles depends on the square of the distance. Q1, Q2 divided by R square. That means if you have a larger radius, larger distance, then your force is weaker. Right? So if you are very far from the positive charge nucleus, you can easily release this electron. Okay? So if you have a sodium metal like this, let's say you have a wire that is made out of sodium. There is thousands, millions of billions of atoms over there. Each atom releases one electron, one electron, one electron. So you have plenty of electrons over here. So you have so many electrons that contribution from the one. So you have, if you have a more charge carrier, then you can pass the electricity easily. Okay, this is like a macroscopic picture. Definitely we're going to talk about this one after like a few lectures also. So basically why the metals, they are good conductors because they have electrons, they can freely move in the crystal or in the wire. So if you have like a charged particle, it can transfer from one point to another point. That means your material is very good for the conducting electricity. Okay, insulator. I mean, you can consider carbon. Carbon. You have a carbon. Carbon. If you take a look on this one, carbon is number 40. what is atomic number 6? If you consider like a carbon, let's talk about carbon. I need to erase over here. Erase. Superconductor. Carbon, if you consider about carbon atomic number is 6. We have a 6 electron and a 6 proton, and you have a 6 neutron, I think, because your atomic number is 12. So atomic weight is 12. So you have 6 protons, 6 neutron, okay, and you have a 6 means you have a first cell. You have a 2, and second you have 4. 1, 2, 3, 4. So this is a closure because you are the second cell. You have a like closed. You cannot release all of these, electron because they are close by, and you cannot release that electron, and so that you do not conduct the. One question for you guys, you don't have to answer me. Have you ever heard about graphite?
A what?
Graphite. Graphite is like a one thing. One material. You have a hexagon of carbon atom, but if you have a single layer of that graphite, you have a graphene. Let me talk about that. Because whenever I talk about this one, I really want to give some knowledge to you guys. Definitely you will get very good grade in this class, but your grade doesn't matter. Your knowledge matters. Okay. So if you have graphite, then you have a hexagon. You might even do some research if you go to like a. This is one of the engineering material. You can make if you have a graphene layer, you can make some bulletproof some material. It's so strong material that even bullet cannot pass through it. It's very highly conducting. It's a very I gonna make it like exactly the same size. But this hexagon is like a same size. You have a carbon. Your carbon atom is this is the carbon atom. As it's a carbon atom. They are arranged in a hexagon pattern. Okay, like that. So it's a single layer. It's like a 2-dimensional material. This is called graphene. Okay, and if you have pencil, the pencil has a graphite. The pencil has whenever you write, it's a graphite. Okay, I don't have a pencil, but pencil, whatever you write, that's a graphite. You can make a single layer using Scotch tape. And you can get the graphene. This material is very, very conducting. Even if it's made out of carbon. I told you carbon is insulator. But if this carbon is arranged this way, you have highly conducting material that is called graphene. And there is no Nobel Prize in Physics a while ago. Okay? And the reason for that, whenever you have a carbon that's arranged in this pattern, there's a hybridization of this orbital takes place, and you have either sp1 or sp2 hybridization, and that gives you some extra charge there. There's a detail about this one you may not have to know, but graphene is one of the engineering materials. It's very interesting from the physics point of view. Why it's so conducting, highly conducting? Why it's like a very strong material? It can even stop the bullet. If you make like some special design, you can make a bulletproof material, something like that. So there's a lot of research going on. So if you continue your education, if you go to a higher level, if you go to PhD or masters, you will hear about this one. Okay, at some point. Anyway. So this is about the division. So I'm gonna go quickly some of the points over here. The Coulomb's law. I already talked about Coulomb's law briefly. If you have two charged particles, they interact each other. So two charged particles, they interact each other by a force. Okay. So the force depends on whether the charged particle is positive or negative. So if you have, let's say, charged particle, you have a positive charged particle. If you have a charged particle, positive, they repel each other. Okay, they repel each other. Okay, you have some distance between them is r. So let's say you have a q1, you have a q2. Okay, but if you have a positive charge and you have a negative charge, or vice versa, so a negative or positive charge. So basically, you have a force, they attract each other. So if the charge is negative and negative, they also repel each other. The charge, the polarity of charge matters, okay? But either these two charged particles, they attract or repel with the force. Force is given by Coulomb's law. The force is given by, according to Coulomb's law, you have K, magnitude of the charge Q1, magnitude of the charge Q2, divided by square of the distance. Okay? And this is the magnitude of the force. Don't be confused. This is the magnitude of the force. Magnitude. These two charged particles, they interact, either they attract or they repel. Okay? And so the force is given by this formula. K is called Coulomb's constant. Okay? K is called Coulomb's constant. K is called the 9 times 10 power 9. Sorry, 10 power 9. 10 power 9. Some people say 8.99, but it's closer to 9. So you can write it 8.99. Okay, it doesn't matter. Or you can even write down 9 times 10 power 9. Okay, we call this Coulomb's constant. Coulomb's constant. Okay, so sometimes you see the same formula in the book, not in terms of Coulomb's constant. You will see in terms of permittivity of free space, but there's a relation between permittivity of free space and the Coulomb's constant. I just write down that. So you have a relation between them is like that. K equal to 1 over 4 pi epsilon naught. Okay. The epsilon naught is like some number 8.85 10 power minus 12. So you have some unit over here. I just skip that unit. It's called permittivity of free space. Permittivity. Permittivity of free space. Okay. So basically, Coulomb's law is very simple. You might have known this law from your high school also, because you must know that the same charged particle, same polarity, they always repel each other. Only the charged particle of opposite sign, they attract each other. Okay, and the force is given by this Coulomb's law. Either repulsion or attraction. The force depends on the magnitude of the charge and square the distance between the charge particle. Alright, so the force, is a vector quantity. Force is a vector quantity, like definitely. If I have two charged particles, one is positive and the other is positive, definitely they repel, and the force is going to be this direction. So if this charged particle they repel, this force is going to be one force this direction and another force is going to be this direction. Okay, so basically it will be equal in magnitude but opposite in direction. The electrostatic force on charged particle 1 can be described in terms of unit vector along the axis through the two particles radially away from the particle 2. Basically, force is a vector quantity, and the direction is like given by the radius vector. Okay, so and the line they are joined by that, you know, r, and the magnitude is given by that. So this is like very simple, you know, like whether they attract or they repel. I'm not going into detail. Definitely, if you have a two charged particles of the same sign, they repel. Two positive charge, they repel each other. Two negative charge, they repel each other. But if you have one positive, another one is negative, they attract each other. So this is what that means over here. The sign matters. Okay. So for example, you have an electron which is negatively charged, and you have a proton as a positive charge, and there's like some checkpoint over here. The figure shows that two proton, symbol P, and electron is symbol E on the axis. On the central proton, you have central proton over here. What is the direction of A? The force due to electron. I mean, you have like a nice, checkpoint over here. I mean, it's very simple. Let's say you have 3 particles. Okay. You have one is electron. So negatively charged. You have one proton, which is positively charged. You have another proton, positively charged. The question is that on the central proton, you are talking about this is the proton, okay? This is the central proton. Central proton. Okay, you have a central proton. What is the direction of the force due to electron? What is the direction of force? I mean, definitely is a negative charge, positive charge. If you talk about this guy, right? Force will be that. Right? If you consider like the same thing about this one, the force will be that, because you are considering that point. And the force due to the another proton, they repel each other, also is going to be. Because if you consider this proton, they are same charge, the force is going to be again this person, right? To the left, right? And see the net force, definitely, because this guy is going to repel, this is going to attract. So basically you have two force that direction. So net force is going to be in that direction, right? So this is like a, just to show that, two charges of the same polarity, they repel. If you have two charged particles of opposite polarity, they attract each other. Alright, so I'm going to give one simple question over here, and then because I need to assign the homework, and I'm going to finish the class. I'm going to give a hint, I believe. Even I can solve it, it's not that difficult. You have a two charged particle, Q1 and Q2, and the polarity is positive. You have a distance between these two charged particles R. And you are considering that the arrangement is in the x direction. Two positively charged particles fixed in a place on the x-axis. Your charge value of this Q1 is given, Q2 is given. The separation value R is given. What is the magnitude and direction of the electrostatic force F12 on the particle 1 on the particle 2? It's a very simple question, but let me solve it for you and finish the class. You have a two charged particle. You have a Q1, you have a Q2, you have positive in x direction, you have an R value. I need to find what is the force on the particle 1, due to this one. This is positive, this is positive. If you consider this guy, definitely they repel. So this guy is trying to move this way, right? Really? So whenever you write the force on 1 due to F1. You need to find F1. So let's find that force. The force value is given by the magnitude of this force. The magnitude of this force is given by F1 is given by the formula K Q1 Q2 divided by R square. Everything is given. Just write that and take it. Just show you how to find the magnitude of force, and this is the magnitude. What is the direction? If you point in that direction, positive. If you point in this direction, X is the origin because you are talking about this point, this Y. You can either consider as positive is like a 180 degree, you can call it, right? Or even if you got a negative X direction, what if the force you got to get over here, you can say negative X direction. Or you can talk about the unit vector. The unit vector is along this one is given I. That should be what is the number? Newton negative I. Okay. Or you can say it's a 180 degree because it's going to be centric because the angle you make this one with the positive X direction 180 degree. Alright, so with that, I gonna grade your test definitely. I'm almost done. So you'll see your grade sometime today. I'll post your homework today. And with that, see you.